Okay, welcome back. Trigonometric substitutions, 8.4. And what are we using these for? Well, when you have an integral that kind of has an element in it like this that you can't necessarily get rid of, that's when you're going to use these subs. Okay, and there's three basic ones. Okay, so to get rid of this square root object in your integral, you'll let u equal a sine theta. In order to get rid of this guy, you let u equal a tan theta. In order to get rid of this guy, let u equal a secant theta. Okay, I usually do like a setup first, and then I go through and kind of figure out the problem. So I think of it like, listing ingredients like you're a baker or something. You need all of this in order to complete the problem, right? Okay, so that's kind of how I attack these. Let's look at number, I don't know. I don't want to look at anything too complicated to begin with. Where are we? We're on 8.4. A basic trig integral. I guess we'll go with one of the examples. Okay, so example one in the book. We have the integral of dx all over x squared times the square root of 9 minus x squared. Right, so this integral is thrown in your lap, and you're kind of looking at it, and you're like, oh, I don't know how to do this. If I do a u sub, it's not going to work. It's not exactly a inverse sine type. It's none of that stuff. Okay, so you'll probably try to do trig sub to get rid of this square root to make it easy to integrate. So when you see this kind of form, a squared minus u squared, you're going to do a u sub u equals a sine theta. Okay, so we'll let u equal a. In this case, a is 3, and then sine of theta. To evaluate this thing, I know that there's some information I'm going to need. I'm going to need du. Okay. So du is going to be 3 cosine theta d theta. Okay, and actually we shouldn't use u. It's just x. Okay, let's just write that as x. We're going to let x, this thing, equal 3 sine theta. Here, dx equals 3 cosine theta. Okay, so this will get the problem started. But at the end, we're going to need to kind of convert back into terms of x. In order to pull that off, you need some extra information. So first, I'm going to solve this thing for theta. Okay, so I would have x equals 3 sine theta. Take sine inverse of both sides. Sine inverse of x. Well, I can't take sine inverse unless I divide by the 3 first. Okay, so I have to say this is sine theta equals x over 3. Okay, so if I take inverse sine on both sides of that, I get theta equals sine inverse of x over 3. Okay. And then what I'm going to do is draw this triangle, because the end expressions are going to be things like, I don't know, so cotan of sine inverse of x over 3. And to simplify those, you're going to build a triangle. So remember, sine is opposite over hypotenuse, so it's x all over 3. And then I could get the third side using Pythagorean theorem, which is 9 minus x squared. That's all the information you need to get this problem done. Okay? And we could, collect it along the side as we go. I think it's just more efficient to get it all out of the way. Let's put it here, and then we can use this for reference as we do the problem. Okay. So anyways, in the first part, you're just working with these two guys. You're substituting that into here, and it'll end up being a trigonometric integral that we kind of got introduced to in the last section. Okay, so dx is 3 cosine theta d theta. X squared is 9 sine squared theta. And then we have the square root of 9 minus 9 sine squared theta. Okay, so what is that? Well, 3 over 9 is the same as 1 over 3. Let's go ahead and pull that out. Then I have cosine theta d theta in the numerator, all over sine squared theta times, and for this part of it, I'm going to factor the 9 out, and I'll have 1 minus sine squared theta, and then maybe you already see, oh, good, the square root's going to go away, because 1 minus sine squared theta, if you use the Pythagorean identity, 1 minus sine squared is equal to cosine squared. So you could rewrite it as sine squared theta times the square root of 9 cosine squared theta, and that's the magic of this method, right? Because now I can get rid of the square root, which is what I want. I get 1/3 integral cosine theta d theta all over sine squared times 3 cosine theta. Let's factor that 3 out in front, so we end up with 1/9 now. And the denominator sine squared cosine theta. The square root of cosine squared we'll just write as cosine theta. Awesome. Then these things go away. I'll have 1/9 integral. 1 over sine is cosecant, so this is cosecant squared theta, d theta. Then, cosecant squared is just the derivative of cotan, but without a negative. So I can easily integrate that. That's negative 1/9 cotan theta plus c. Okay, and now I have to go back to this information. Okay, so this is really negative 1/9 cotan of sine inverse of x over 3. To evaluate cotan of sine inverse, in other words, cotan of this angle, you could use this triangle. Okay. Cotan of this angle is the ratio of sides of this right triangle. So cotan, remember, is adjacent over opposite. So I could replace cotan of theta with square root 9 minus x squared all over x. And I get a nice algebraic form for my integral. Negative 1/9 times the square root of 9 minus x squared all over x plus c. And that's pretty much it. Okay? You can multiply that out and make it look nice. But that's the idea. Okay? Okay. So the rest of it is just kind of variations on this idea. Let's dive in and look at some of the problems. Okay. So maybe example 2, I guess. So we want to find the integral of dx all over the square root of 4x squared plus 1. Okay, if you look back at our initial kind of statement, we're presented with an integral that has this form in it, and we're trying to get rid of that thing. Okay. So we'll do a u substitution. U equals a tan theta. Okay, so a is 1 in this case, and then the u is 2x, right? Because we could rewrite it as dx all over the square root of 2x squared plus 1. So that's what our u is. And then this is our a squared. This is u squared, and then this is a squared. Okay, so let u equal 2x. So we'll have 2x, and then we're saying that's equal to a times tan theta. So a is 1, and then tan theta. So I need to go through and get all my information required. I'm going to divide both sides by 2, so I get x equals tan theta all over 2. And then the dx is equal to secant squared theta all over 2 d theta. So that will get me started. Then I'll need that triangle information. So working with this first expression, take tan inverse on both sides. And what do you get? Well, you'll get theta equals tan inverse of 2x, which is the same as 2x over 1. I'm writing it that way because I'm going to take advantage of ratios of sides of right triangles to reinterpret this, right? So tan of 2x over 1, tan is opposite over adjacent, so the opposite is the 2x and the adjacent is 1. Then I can use Pythagorean theorem to get the third side, which will be 4x squared plus 1. And then there's my ingredients, right? That's my, so I need to go to here. Okay, so first you start with this information, plop it into here. So we'll have the integral of dx, which is secant squared theta all over 2 d theta, all over the square root of 2x squared, which is basically tan squared theta, and then plus 1. Okay. I can factor a 1/2 out of this thing. That'll help a little. We have the integral of d theta, secant squared d theta, all over tan squared plus 1 is the same as secant squared. Okay. So this should turn out real nice. So I have 1/2 times secant squared theta d theta. Then the square root of secant squared is just secant theta. Oops, not secant squared, but just secant. Secant squared over secant is just secant. And then we have a well-known formula for that. It's 1/2 ln absolute value secant theta plus tan theta plus c. Of course, we started in x, so we want to end in x. So now we use the triangle. Okay, so now I go back to my triangle. I have 1/2 ln of secant of this angle. Secant is 1 over cosine. Okay, so that'll be hypotenuse all over opposite. Oh, sorry, hypotenuse over adjacent. So it's just square root 4x squared plus 1. Plus tan of this triangle, so it's opposite over adjacent, which is 2x. And then plus c, and then that should be the answer. Okay, let's look at, I guess, example 3. Okay, they want us to figure out the integral of dx all over x squared plus 1 to the 3/2. Okay, this doesn't look like it conforms to our substitutions, right? I'm not seeing a square root anywhere, but it's there. Right? 3/2 is basically this thing cubed, but then the square root of it. Right? So there is that form involved. We have the a squared plus u squared form, or u squared plus a squared in this case. So u is just the x. So I let x equal 1 tan theta. And then I go through and get all my info. Okay, so dx will be secant squared theta d theta. If I solve for theta in the first equation, theta equals tan inverse of x. I'll write x as x over 1, so I can build my triangle. Okay, so tan inverse, the input is opposite over adjacent, and then my third side will be x squared plus 1 by the Pythagorean theorem. So I have all my junk together. Now I use the first 2 bits and plop it into here. Okay, so this will be the integral of secant squared theta d theta all over x squared, which is now tan squared theta plus 1 to the 3/2. It'll be secant squared theta d theta all over secant squared theta. Tan squared plus 1 is secant squared to the 3/2. This will be the integral of secant squared theta d theta all over secant squared to the 3/2. You multiply the exponents. 2 times 3/2 is 3. So I end up with secant cubed theta in the denominator. Then that'll equal d theta all over secant theta. 1 over secant theta, you know, if you're not sure, convert things to sines and cosines because we're more familiar with that. 1 over secant is cosine theta. And then I know how to integrate that. Integral of cosine is just sine. And then use the triangle to get back home. So the sine of this angle is opposite over hypotenuse. So we just end up with x all over square root of x squared plus 1 and then plus c. There's our answer. Okay, let's try one where we have to actually evaluate the critter. Okay. This would be an example, I guess, 4. And we have the integral from radical 3 to 2 of square root x squared minus 3 all over x dx. Okay, so the form this time is a sine inverse. This is u squared, so u is x, and then the a squared is 3. So a is actually root 3. So root 3, x is equal to root 3, and it's not sine sub, it's secant, right? Root 3 secant theta d theta, root 3 secant theta. Then I need my information, so dx is root 3 times secant theta tan theta d theta. Right, then my triangle stuff, so secant theta equals x over root 3, so theta is secant inverse of x over root 3. And then my triangle, secant is hypotenuse all over adjacent. So the last side by the Pythagorean theorem would be x squared minus 3. Okay, so let's dive right in. I get the square root of x is 3 secant theta, so x squared is, so x is root 3 secant theta, so x squared is 3 secant squared theta minus 3. X is, again, root 3 secant theta, and then times dx, which is root 3 secant theta tan theta, d theta. Okay. Do some cancellations. Up top, I'll have 3 times secant squared theta minus 1. Down below, these guys are at least going to cancel. These guys are going to cancel. I guess we just have 1 down there, and then times tan theta d theta. This will be the integral. There's a root 3 there, okay, so I can pull that out of the integral altogether. And then secant squared minus 1 is tan squared. So this will just be the square root of tan squared theta times tan theta d theta. That'll be root 3 integral, the square root of tan squared is tan. Tan times tan is tan squared, theta d theta. And then to deal with those, you just convert using Pythagorean identity. Tan squared is secant squared minus 1. And then you'll have root 3 times the integral of secant squared is tan theta minus theta. And we have to remind ourselves to evaluate eventually. You can evaluate right now by plugging these guys, into your formula for theta. Okay? So if you did that, if you put 2 into x for that upper limit, you would have secant inverse of 2 over root 3. Right? So that would be the same as asking the question, secant of what angle is equal to 2 over root 3? Okay? So that's going to be pi over 6. And then if you put in root 3 into here, you're asking the question, the secant of what angle is equal to root 3 over 3? In other words, the secant of what angle is equal to 1? And that would be 0. Okay. And then we could plug it into here, and I guess we don't even really need the triangle if you do it this way. You just have root 3 times tan of pi over 6 minus pi over 6, and then minus 0 minus 0. I just have to figure out tan of pi over 6 really quick. So sine of pi over 6 is 1/2, and then, so it's 1 over root 3. In other words, it's root 3 over 3 minus pi over 6. I still have to remember that little curve. So tan of pi over 6 is that. Then multiply it out. So root 3 times root 3 over 3 is just going to be 1 minus pi over 6 root 3. Okay, you could do it the other way. The book will go through that for you. I can go through it real quick, I guess. So the other way would be, instead of changing the bounds, use the triangle to change back, right? So it'd have square root 3 times tan of theta using this triangle. Tan is opposite over adjacent, so you'd have radical x squared minus 3 over root 3. And then minus theta. Theta is just, there's not much you can do there. It's just secant inverse of x over 3, or x over root 3, rather. Okay, and then we evaluate from root 3 to 2. So you have to convert everything back into x, and then you could use the original bounds. If I, okay, so if I put in 2, I get radical 4 minus 3, so radical 1, which is 1 over root 3, minus, if I put 2 into here, 2 over root 3, secant inverse of that is 1 pi over 6. Okay. And then minus, if I put root 3 into here, I get root 3 squared is 3, minus 3 is 0. And then minus, if I put root 3 in here, secant inverse of root 3 is just 0. So you get the same answer, is long story short. You get 1 minus pi over 6 root 3. Okay, pretty much everything else is just kind of variations on the theme. Identifying what is used. Sometimes you can have some pretty ugly integrals resulting. Some of these you have to complete the square on. Let's just look at really quick 37. The integral of dx all over the square root of 4x minus x squared. Right. So they're hoping you realize, okay, I have to complete the square. So this is square root of negative x squared minus 4x, and then I have to add in negative 4 over 2 squared is positive 4. So I've really added in a negative 4. I need to then get rid of it by adding 4. Okay. This thing then becomes the integral of dx all over the square root of 4 minus x minus 2 squared. And then you're thinking, oh, I can do a trig sub. Don't do a trig sub if you don't have to. There's maybe one lesson to be learned from this example. This is a sine inverse form. So the a value is 2. The u is just x minus 2. So it's sine inverse of u minus 2 all over 2, or x minus 2 over 2 plus c. Okay. So in this case, there's not really even a need to do trigonometric substitution. Trig subs are such an annoying thing that you don't want to have to do them unless you absolutely positively necessarily have to do it. So avoid them, usually at all costs, but sometimes push will come to shove and you have to man up, so to speak. Okay, so there's that. Thanks for watching. We'll see you next time.